So first, in order to motivate the comparison tests, we're going to think about the following series. So this is just going to be another infinite series from n equals 1 to infinity of 1 over n to the power 3 plus 5. Now, some things to consider, of course. We're handed an infinite series. We're asked, does it converge or diverge? We do the test for divergence by introducing the limit. If we do the test for divergence, we'll see that the limit of our series generating function, the 1 over n cubed plus 5, that just goes to 0. If we ask ourselves, well, is this a geometric series? The answer here is no. So it looks like in our arsenal of convergence-divergence tests, the next logical thing for us at this point is actually the integral test, which we just covered last class. And I'm not going to dive into the full nitty-gritty of integral tests here, but of course for integral tests, we'll rewrite our function f of x in terms of the series function by replacing the n's by x's. So this is 1 over x cubed plus 5. And we need to make sure that this function f of x is positive, continuous, and decreasing. I'm going to spare us the proof of those three things here and just say, you can go ahead and check this, and this function will satisfy all three of those. So if we actually dive right into integral test, we take the integral from 1 to infinity of 1 over x cubed plus 5. We introduce the limit to take care of that infinite bound. We immediately then see we are stuck in a pickle. Because once we introduce the limit, the next thing we get to do is find an antiderivative for that integrand. And well, finding an antiderivative for this integrand is actually very tough. So immediately, just by going through our series tests at our disposal, well, we can perform integral test here, but unfortunately, finding the antiderivative might prove impossibly difficult. So we're going to ask ourselves basically the next question: is there an easier way? And by easier way, what I mean is, can we get around doing this integral? In other words, can we get around doing the integral test? And well, you might have guessed it, the answer is yes, and this is where the comparison tests are going to come in. So if we're thinking about that function, or the series 1 over n cubed plus 5 from n equals 1 to infinity, we're going to attach this by a comparison test. And we're going to dive into the nitty-gritty of comparison tests in the next video, but this is just to kind of give you an idea of where we're going to go. So for example, we don't know anything about this particular series as it stands. For comparison tests in general, we're going to try and think about how our series that we're given relates to maybe a p-series or a geometric series that looks similar. To the series that we're handed. So it's going to be critical that we understand both p-series and geometric series for doing comparison tests. And this is what I mean when we're going to try and compare our series to one of these two types of series. So if we maybe squint our eyes, our series is the series n equals 1 to infinity, 1 over n cubed plus 5. If I tell you, you know what, we're going to try and look at this like a p-series. It's not a p-series, so maybe I shouldn't even write that at all. Let's go ahead and erase that. What I am going to write is that this almost looks like a p-series. Okay, Okay. And the only little hiccup with this not being fully a p-series is this plus 5 right here. So basically what I want to say is a p-series that looks very similar is, hopefully you can see, the series from n equals 1 to infinity of 1 over n cubed. Again, this is our actual p-series. We're not taking our original series and rewriting it as a p-series. I'm just saying our original series, it almost looks like this p-series 1 over n cubed. And hopefully you remember, since p equals 3, which is greater than 1, this converges. So the two bits of information we have so far is, number 1, looks almost like a p-series. The second is the p-series it looks like, the n equals 1, oops, doesn't like that, n equals 1 to infinity, 1 over n cubed. We know that this converges. So these are the two bits of information we sort of have so far. And well, let's talk about why this is actually going to be useful. So again, we have our original series, n equals 1 to infinity, 1 over n cubed plus 5. And we have our p-series comparison, which is a series n equals 1 to infinity of 1 over n cubed. And well, where we're going to go next is actually say, can we compare these? In other words, can we take these series functions, 1 over n cubed plus 5 and 1 over n cubed, and can we compare them, as in set up an inequality? So hopefully you recognize that, well, since the denominator on the left side fraction is larger, that means that that overall fraction is smaller, since both fractions have the same numerator. So we can pretty easily see that in this case, the left-hand side is less than or equal to the right-hand side. So what we've just shown basically is, for all n, this inequality is true. As in n equals 1, 2, and so on all the way to infinity. Well, if this is true for all these n's, we can then say, you know what? The original infinite series, 1 over n cubed plus 5, that sum has to be less than or equal to the sum of the series on the right-hand side. And here's the interesting thing. We know something about this series on the right-hand side. We know that this converges. The other thing we know is this series on the left-hand side, this has to be greater than 0. So in other words, this series on the left-hand side, the sum is stuck between 0 and the sum of the series on the right. So it must also converge. So this is just one example of the comparison test. Again, we went through a lot of the nitty-gritty with this test very, very quickly. In the next few examples, we're going to come up with a more standardized approach of how to think about comparison tests. But hopefully you see the point here where if we can take our original series and say that our original series is less than a known convergent series, it must also force our series to be convergent, as long as our series is positive. The opposite will also be true, that we'll see coming up. If we can prove that our series is always larger than a known divergent series, then our series must also diverge. Let's check it out in examples to come.